Longest increasing subsequence. How do you find order in chaos? Longest increasing subsequence is a Pattern Mastery 100 and interview favorite. Regularly asked at Amazon, Microsoft, and Google, because it tests whether you can spot patterns and optimize solutions. Most candidates start with brute force and get stuck. But if you learn the right DP or binary search trick here, you'll be ready for any sequence challenge interviewers throw your way. Let's break it down. Given an array of integers, find the length of the longest subsequence where each number is strictly greater than the one before it. Remember, a subsequence can skip elements, but order matters. Let's assess the options. The brute force approach tries all possible subsequences. Exponential time. That's not scalable. The classic DP approach is O(n)(. For each element, look at all previous elements to find the longest subsequence ending there. But with patience, you can improve to O(n) log n. Using binary search, maintaining a tails array where each value represents the smallest possible tail of an increasing subsequence of that length. Let's start with a DP approach for clarity. Create a DP array of the same length as nums, filled with ones. Each element is an LIS of at least 1. For each I from 1 to n1. For each j from 0 to i1. If nums I greater than nums j, set dpi equals max dpi, dpj, plus 1. The answer is max dp. Let's approach, dynamic programming, O(n)(, time complexity, O(n)(. This line defines a class named solution. In Java, every method must live inside a class, so this is just the container for our logic. Short pause before we step inside. Here we define a method called length_. It takes an array of integers as input and returns an integer. This integer will represent the length of the longest increasing subsequence. Think of this method as the main machine that solves the problem. This line stores the length of the input array in a variable called n. Instead of recalculating the array length again and again, we store it once for efficiency and readability. Here we create a new array called DP. Each position in this array will store the length of the longest increasing subsequence that ends exactly at that index. You can think of DP as our memory or notebook where we save intermediate results. This line fills the entire DP array with the value 1. Why 1? Because every number by itself is an increasing subsequence of length 1. This is our base case and the foundation of the dynamic programming approach. We initialize a variable called max to 1. This variable will keep track of the overall longest increasing subsequence found so far as we move through the array. This outer loop goes through each element in the array one by one. For every position I, we are going to calculate the best increasing subsequence that ends at that position. This loop runs n times. This inner loop looks at all elements that come before index I. We only compare with previous elements because a subsequence must move forward in the array. This nested loop is the reason the time complexity is O(n)(. Pause here. This is the core of the algorithm. This condition checks two things. First, it ensures the sequence is increasing by confirming the previous number is smaller than the current one. Second, it checks whether extending the subsequence ending at j would give us a longer subsequence than what we currently have at I. If the condition is true, we update dpi. This means we found a better increasing subsequence ending at index I, so we store its new length. It's like saying, this path is better, let's keep it. After finishing all comparisons for index I, we check whether the current subsequence length is the longest we've seen overall. If it is, we update max. This keeps our final answer accurate. This closes the outer loop. By this point, we've evaluated every possible increasing subsequence ending at every index. Finally, we return max, which holds the length of the longest increasing subsequence in the entire array. This closes the method, and this closes the class. Final wrap-up. And that's how this algorithm works. It first sets up a dynamic programming table with default values, then systematically compares each number with all previous ones to build longer increasing subsequences. Efficient, simple, and elegant. Test case check, LIS using dynamic programming. Let's test our function using this input. 10, 9, 2, 5, 3, 7, 101, 18. These numbers represent a sequence of values, and our goal is to find the length of the longest strictly increasing subsequence hidden inside the array. Here's why the solution works. Our DP array, dpi, represents the length of the longest increasing subsequence ending at index I. For each number, we look back at all previous numbers. If a previous number is smaller, and extending its subsequence makes ours longer, we update our dpi value. This way, we gradually build up all possible increasing subsequences. In this specific example, one valid longest increasing subsequence is 23718, which has a length of 4. The DP computation captures this perfectly as it iterates. And that's exactly what our program outputs, 4. The result matches the expected value, confirming that our DP logic is working correctly. Wrap up. So, our implementation is correct. The algorithm successfully computes the longest increasing subsequence using dynamic programming, efficient and accurate. Approach: patience sorting, binary search, O(n) log n, time complexity, O(n) log n. This line defines a class named solution. In Java, every method has to live inside a class, so this is simply the container for our logic. Think of it like naming the folder that holds all the instructions. Here we declare a method called length_offLIS. It takes an array of numbers as input and promises to return a single integer, the length of the longest increasing subsequence. This is our main entry point. This line creates an array called tails. Its job is to track the smallest possible ending value of increasing subsequences of different lengths. You can imagine tails as a set of piles where each pile represents a sequence length. Here we initialize a variable called size. This keeps track of how many valid piles, or increasing subsequences, we currently have. In other words, this will eventually become our answer. This line starts a loop that goes through every number in the input array one by one. Since we scan the array once, this part contributes a linear pass, or O(n), to the solution. Here's the key optimization. We use binary search to find where the current number x should go inside the tails array. Because binary search is used, this step runs in O log n, time, which is what gives the algorithm its overall O(n) log n, efficiency. If the number isn't found exactly, Java returns a negative value. This line converts that result into the correct insertion position. Think of it as translating a not found message into here's where it belongs. Now we place the current number x into the correct position in tails. This either replaces a larger number or extends the sequence in the most optimal way possible. If the number was placed at the very end, it means we found a longer increasing subsequence than before. So we increase size by 1 to record this growth. This closes the loop. By now, we've processed every number and updated our piles efficiently using binary search. Here we return size, which represents the length of the longest increasing subsequence found. Notice we never built the full sequence, just its length. This closes the method definition. And this final brace closes the class. And that's how this algorithm works. It first sets up a structure to track optimal subsequence endings, then uses binary search to place each number efficiently. Efficient, simple, and elegant. Test case check. Optimal LIS, binary search plus patience sorting. Let's test our function using this input. 0, 1, 0, 3, 2, 3. These numbers represent a sequence where we want to find the longest strictly increasing subsequence hidden inside the array. Here's why the solution works. We maintain a subseq array that stores the smallest possible tail for an increasing subsequence of each length. Using bisect_left, we either append a new number when it extends the sequence, or replace an existing tail with a smaller one, keeping future options open. And that's exactly what our program outputs, 4. This confirms that the optimal patience sorting method calculates the LIS correctly for this test case. So, our implementation is correct. The algorithm successfully computes the longest increasing subsequence using binary search and a compact tail array, efficient, accurate, and reliable. Longest increasing subsequence. Let's do a recap. We started by understanding the goal. Find the length of the longest subsequence where each number is greater than the previous one. The key detail: it's a subsequence, not a subarray, meaning we can skip elements, but must keep the order intact. Assess recap. We compared different approaches. The brute force method checks all combinations but quickly becomes impractical. The dynamic programming approach, with O(n)² complexity, gave us a structured and efficient way to build solutions step by step. And we discussed how an advanced binary search technique can push that to O(n) log n, for even larger inputs. Structure recap. Our DP plan was simple. For each element, look back at all previous ones and track the length of the longest subsequence that could end there. Each number starts as a sequence of length 1, and we update those lengths as we find valid increases. Implement recap. We implemented this logic cleanly in code, ensuring each element's LIS length was computed correctly and ran the function on LeetCode without any syntax or logic errors. Check recap. After running the test case, 0, 1, 0, 3, 2, 3, we confirmed our output was 4, matching the expected result. Our approach passed all test cases successfully. Closing insight. The big takeaway? Pattern problems like this reward structure over guessing. Once you understand how to build solutions incrementally, or even optimize them with binary search, you'll start to see order emerge from the chaos every time.